Hi, this is an example problem about a leaky water tank. This is from chapter 11 and involves ideal fluid flow. So we see we have a tank there, and you can see that it's opened at the top and it has a hole below a distance h, and water is flowing out. We're going to be using the equations for ideal fluid flow, so Bernoulli's equation and also the equation of continuity together to solve this problem. Now, we've seen in a previous video how there's four variables shared between Bernoulli's equation and the equation of continuity. That's the cross-sectional area of the fluid in the flow, the speed of the fluid, the height of the fluid, and the pressure of the fluid. And we've got two different spots. We can label them if we want 2 and 1, as we did over here. So there's your 2, there's your 1. And we're going to try to figure out AV, YP for each of these. First thing to notice is the A, the area, that's the cross-sectional area. So as you think of that, that's kind of like, right, this area above, and then over here it's that little area there. Now, we don't know what those areas are, but we can write them down. So A2, we don't know. A1, we don't know. What about the velocities? We're trying to figure out the speed exiting, right? So we want to know what V1 is. V2, we don't necessarily know what it is. The height, well, we get to choose a 0 point, right? They've already chose 0 at the lower position, which makes a lot of sense. So let's call this one 0, which makes this one h above 3 meters above 0. And finally, we've got the pressure. You'll see in the picture that the pressure P0 is the same at the top and the bottom. And that's because at the top and the bottom, the fluid, the water, is open to the atmospheric pressure. Whenever you have a fluid or two fluids, the water and the air, and they are at an interface, they are meeting each other, their pressures will equalize. So these are both at atmospheric pressure, P atmosphere, whatever that is. So we've got this information. Now the first thing I want to do is use the equation of continuity to get some idea about the speed of these. So equation of continuity is going to tell us this. So I've got the speed at point 2 times the pressure times, the area at point 2. In other words, the volume flow at point 2. It's going to be equal to the volume flow rate V1 times A1 at point 1. Now I'm going to go ahead and just do a little bit of algebra here. Let's say we divide V1 by both sides. We also divide A2 by both sides. Now, if we compare the areas here, right? Here's A1. Here's A2. Which one's bigger? Oh, A2 is way bigger than A1, right? This is huge. This is tiny. Effectively, this is going to be equal to 0. In other words, the speed of the water up here is going to be really small. We can say that this is effectively 0 here. So we know what V2 is. Now we're going to go ahead and we're going to use Bernoulli's equation to be able to solve for V1. We can't get V1 out of the continuity equation because the 0 here is an approximation. But let's go ahead and look and see how we can get it from Bernoulli's equation. So we're going to go ahead and use this and write it down. So since we're solving for V1, we'll start with that one first. P1 plus 1/2 rho 1 V1 squared plus rho G Y1 equals rho, write the same thing again. P2 plus 1/2 rho V2 squared plus rho G y2. We've got all our data up here. Let's see what we know here. So we've got the same pressures, right? They're both atmospheric pressure. I can subtract those off. Since they're the same, they'll cancel. Now for y1, we set that term, the height there at 0. That's gone. And so now we can just do a little bit of simplification here. We're going to end up with 1/2 rho v1 squared equals 1/2 rho v2 squared plus rho g y squared. Let's multiply both sides by 2 divided by rho. And when we do that, we will of course cancel these things out here. We'll be left with v1 squared, and that's going to be equal to, let's see, we can go ahead and distribute. Let's distribute the rho. So if I distribute it to the first term, I'll cancel the 2. I'll cancel the rho, and I'm going to just get v2 squared. And when I distribute that to the next term, I'm going to go ahead and cancel this rho, and then I'm going to get a factor of 2g y2. And finally here, we're going to go ahead and, oh, we forgot to say, right, that the velocity v2, we said, is effectively 0 as well. So, okay, we can do that. There we go. And finally, we can get our final form here. v1 is equal to the square root of 2g y2. This is sometimes called Torricelli's equation. We've got all the information here. We can go ahead and plug it in. So 9.8 meters per second squared, and the height y2 there, 3 meters. When we plug this into the calculator, we get a value of about 7.7 meters per second.